option.
It's like the worst. Right at the
Okay, here we go. So last time we discussed 1 and 2, yeah?
Yeah, I know. Well, yes, we did. We talked about that.
So we didn't write anything down for 1 or 2?
Yeah, we did.
Oh, very good.
Oh, we did for 1.
So the key idea is that, hey, the key idea is that, as it shows in your notes, number 2 is identical to number 1. I put those both on just so you would remember that if you're finding the average velocity of a particle, average velocity. Yeah, that's the average rate of change of position, which is the same thing as finding the secant slope of a position. So those are exactly the same thing. So you really don't have to write something extra for number 2, you just have to remember that they are the same thing.
What does RSE stand for?
Rate of change. Questions? Ellie or Liza asked about the quiz and like a review packet. The review sheet for the quiz really is just the problems in the buff, pink and yellow packet. Like all I did for the quiz is I took 2 questions like from those 3 packets and I just modified them slightly. It's just the purpose of the quiz is just for me to verify that you have really retained what you have to write when you're doing a written section of an AP test. So you remember what they're going to require as far as the written portion. So really, if you just study what's in those 3 packets, you're in good shape. So if you can do every problem in those 3 packets, you'll be just fine on the quiz. So, does that answer your question?
Yeah.
Okay. Other questions on 1 or 2? Okay, cool. Did we do 3 at all?
Yeah.
Oh, please.
I have a question,
Yeah.
just to kind of re-explain the graph again, just like the moving left and right and the up, not up and down, but like the positive and like negative, just to like, I guess, refresh my brain.
Just kind of a quick review.
Yeah,
Is that
just
what
of
you're
like how the particle is like.
So do this. Let's get the roll fast. Hold on. That's it. Cool. Okay, quick refresher then. So this is the position graph, and basically what you want to remember is don't try to. My advice is don't follow the curve. Just follow the numbers. And every dot has 2 numbers assigned to it. The first number is the time, and the second number is the location. So if I click here. So that's -1, 13. That means the time would be 1 second before we started keeping track of time, so just 1 second previously. And the particle would be at location 13, which means along this line which the particle moves, so out here in front, instead of the center of the path is 0, 13 would be just a little bit to the right of the center. You come to this dot here. Now we're 3 seconds into the particle's life, and it's sitting over here at -75, so it's way to the left of the center. Is that enough for now?
Yeah, that works.
2 more. So back to here. Did we do anything on number 3?
Yeah.
So we're done with 3. Cool.
Wait.
Yes, no?
We started.
Started it?
But you said that we filled out with all.
Let's do it real quick. So it says use graph A to estimate the tangent slope of the position graph at the following times. Okay, so the key idea is that you have 3 different formulas that are being graphed. You have the position in blue, you have the velocity in orange, and then I don't have a red color. You have the acceleration in red. The position values are not calculated in this problem. The position values were just created. So I basically just experimented with different formulas until I got a picture that I liked. So that's where these come from, the position values. But I did not create the velocity values. The velocity values were calculated from the position, because you have on your sheet right here that the velocity can be calculated by finding the instantaneous rate of change of the position or the tangent slope of the position. Those mean the same thing. Instantaneous rate of change of position or tangent slope of the position. So I don't know if I showed you this or not, but the way that works, I have to use my keypad here for a second, is if we're trying to find, so we know that at time 3, the particle is located at location -75. And we want to know how fast is the particle moving at that moment. The particle is for sure moving, because if you look at dots close to that, like we come here and we slide along, you can see that the position is becoming increasingly negative. So the particle is definitely moving to the left. What we want to know is how fast is the particle moving to the left right at time 3. And we talked about last time that we can find out, for example, the average velocity between, say, this time and this time. We did that last time. We can find that average velocity by finding the secant slope between those points. So we could do this. Get this to pop up here. This one. So that red line is the secant slope between 2 different positions. And the slope of that red line is the average velocity of the particle between those 2 times. That's what we did in number 1 here. So we go back to here and get these out of the way. So average rate of change of the position is just the secant slope of the position. And if we calculate that, this is what we found. Those numbers are a little different than the ones we did, because we just I kind of estimated, and later I did it a little more precisely. But anyway, the dilemma is, how do we do the same thing at one point? Like, how do we find how fast the particle's moving right at that spot right there? And the problem is, we don't really have any way to calculate how fast the particle's moving, because we only have one point. To find the average velocity, we had 2 points we could compare, but at one point you don't have 2 points to compare. So here's what Isaac Newton did. He said, well, I want to know how fast the particle's moving. You can just watch the board here, okay? I just have to get my mouth. We want to know how fast the particle's moving right at this time right here, time 3. We know the particle is located at -75, and we don't know how fast it's moving. So he theorized that if we just zoom in, get really close to the particle, not close to the particle, close to that time on this data here. Just keep going in closer. And there are always more dots. So what he did is he found this dot here is at exactly time 3. This dot is very, very close to time 3. This dot is just slightly more than time 3. So So he found the average velocity between these 2 points. And then he finds the average velocity between these 2 points. They're not the same, but they're really close. And then he does what we did with limits. He said, well, what if this time, instead of being 2.9999, it becomes 2.9999999? You know, what would be the result? And this time becomes 3.0000001. And he discovered that these two, the slopes between here get closer and closer to being exactly the same. And in the limiting sense, he declared and proved that you can calculate the velocity at time 3 by taking the limit of those two different average velocities. So an instantaneous velocity, back to here, so instantaneous velocity is calculated by measuring really the average velocity between 2 points that are infinitesimally close. The same way that average velocity is found anywhere else. But we say that when we do that, when we find that limit, we're finding the tangent slope of the position. Questions about anything to that point?
And secant is like over a certain average.
So a secant slope is always a slope between 2 points. So if you go back to here, for Liza, he's finding the secant slope between this red and this black dot.
Okay.
And then he's finding the secant slope between the green and the black. So each of those is an average velocity, but then he takes a limit. He makes those points get closer and closer and closer. So they're always finding a secant slope, but the limits value is the value of the tangent slope. So the tangent slope is really just the result of doing a limit on two secant slopes. Other questions? Yeah, please.
I can get it back in.
Yeah. So anyway, the velocity graph is created by doing that point by point. So if you go here, we turn back on the velocity. Let's see where we go. So we've got to zoom back out now. Hold on. Use my mouse. I don't know if that's secant line. Okay, so you see the blue, that's our position values. The orange is the velocity values. If you go dot by dot right here, at this moment, the particle is located 3 left of the origin of its path. At that exact same moment, the particle has a velocity of -10, which means if you put a ruler up on this graph, and you measure the slope of a line that's going right through this point right here, you'll find that slope to be -10. The slope of the position is where the velocity values come from. They go to the next dot, like here. So at time 2, the particle's at location 26 negative. At that moment, the particle will have a velocity of -37 meters per second. Meaning the slope of this blue curve right there is -37. Questions?
Can you say that one more time?
Huh? So every dot always represents 2 numbers.
Right.
So Liza, what is the first number here representing?
The time.
Always the time. And because this dot is on the velocity graph, the second number is representing how fast the particle is moving at that time.
Okay.
So the negative means the particle is moving to the left. Keep the negative and the 37 separate. The 37 means at that moment when the particle's sitting, so I'll act it out again. So at that time, the particle's at location -26, and then it wants to be moving to the left 37 meters in the next second. Other questions? Yeah, please.
Is it specific that we have to do 37? Because I wrote down 38 before.
Good enough. Because you have no way of using the computer, you just have to look at the graph. The point is not to be exact. That's why it says estimate. So that's plenty good, Caleb. So. Anybody else?
And this same rule applies for blue, for acceleration?
For the red?
Like the slope of velocity will always be equivalent to the...
Correct. I believe I said last time that once you understand how the position relates to the velocity, you really don't have to learn anything new. The velocity relates to the acceleration in exactly the same way. Yeah, so if we go to the orange graph, like, I don't know, like right here, I think we did a little bit of this last time, and you find the slope of the orange right here, that slope is 0. That's why this y value on the red graph has a y value of 0. Good. 2 more for August. Anybody else? Okay. Oh yeah, please.
So why on the red and the orange at time is 1.750 with that line in the middle? Explain like the red and the orange. Why is the red at the very bottom of its traveling distance, I guess, and the orange continues to go down?
You're wondering why the orange is going down this way and the red is doing this.
Yeah.
Okay, the red is describing how fast the orange is changing, and here's what's happening. Through here, the orange is becoming more and more negative. So the acceleration values have to be negative and becoming more and more negative to reflect the fact that this is becoming more and more negative. At this moment, the velocity starts to become, I mean, it's still getting negative, but it's doing it at a slower rate. It's like becoming negative more slowly. So the acceleration is still negative, but it is less negative to reflect the fact that this is becoming less negative. That was not a very good explanation. Another way to look at it is this. That's terrible. The slope of the orange right here is some negative number. That corresponds to this y value. The slope of the orange here is actually still negative, but it's less negative. That's why this y-coordinate is less negative than this y-coordinate. This slope of the orange is greater than this slope of the orange. Can you see that? So these y-coordinates have to be negative to reflect these slopes, but this slope is more negative than this slope, and that's why it's turning, kind of. I don't know, 2 points. Terrible. So you're going to fill out that table just by doing what we just talked about. The homework will be the blue. Does anybody have any question on how to fill out the table? We're going to see another example. Okay, number 4. 4 says use the graph to determine when the particle changes direction. Whenever the velocity is negative, that negative indicates the particle is moving left. So for all of this, so to go between 1 and 5, so from here to here, this is the only time when the particle changes from having a negative velocity to having a positive velocity. That means that is the only time when the particle will change direction in that 1 to 5 second window. Questions? Yeah, please, Cassie.
This is actually about the table, but how did we get the top numbers again?
So the top numbers, that was my flaw. I meant to type those in before I made the copies. That's not anything to do with you. They were supposed to be there. So, yeah, 2 more. Anybody else? Please.
So finding when the particle changes direction, so Why do we use the velocity graph and not the position?
You can use either one, technically. On the AP test, it's much more common to have you use the velocity graph. But you can determine if the particle's changing direction by looking at the position as well. They just more frequently will ask you to do it using the velocity. Like, 2 more, please, Clark.
Can you pull up your graph, the box and what you can fill in?
Oh, the box, gotcha, hold on.
That's it, I'm sorry.
This one?
And you said that's for the amount?
So,
The blue line.
we're supposed to be finding the tangent slope of the blue, and what we've talked about, just barely, and now you're gonna memorize is the tangent slope of the position graph or the tangent slope of the blue is exactly the same as the y-coordinates on the velocity graph. So if I go here, Clark, to like time 3, I look at my position graph at time 3. I'm trying to find this slope right here.
Yeah.
That's not the easiest to calculate per se, but because I have the velocity graph, I can just go find this y-coordinate.
Yeah.
And at this point, I'm just asking you to kind of estimate. So it appears to be about negative 59. I think in reality it was slightly different, but not much. Time 3, negative 58. So 2 more.
How do you use the velocity graph, like the line, to find when the direction changes? Like, how would you know with the velocity?
So again, when you look at the velocity graph, just pay attention to the numbers. So what is this number telling you right there, Ellie? 1 comma negative 10. What's the 1 mean?
The time.
Just the time of this story. The negative 10, keep the negative and the number separate. So negative means the particle's moving left. 10 means at that moment the particle wants to be moving 10 meters every second. As you go forward in time, like to time 1.5, is the particle moving left or right? Still left, because at that moment the velocity is still negative. If I keep checking each moment in time as I go forward, the particle's still moving left. It is going faster now. It's not until I get clear to here that the velocity changes from being negative to being positive. And that's the moment when the particle stops moving left and starts to move to the right. I don't know if I answered that. 2 more. Please.
Will we ever be asked to graph the velocity from just looking at the graph of the position?
I've never seen them ask you to do that. They will ask you to answer questions about one graph by looking at the other, which is partly what you're doing right here. You're saying, how can I look at the velocity graph alone and figure out when the particle changes direction? TJ said, can't I just look at the position? And you can. But on a test question, look at me, everybody. Right now I'm showing you all 3, so you can see how they correspond to each other. But on a test, they'll only give you 1 of the 3. And then you answer questions about the other 2 by looking at the 1. So, please, just stretching. Cool. Yeah, Cassidy.
Let's do when it's at 4.5, it's moving positive, but it's still negative. So is that where it switches?
So, at time 4.5, like right here.
Yeah.
So a couple things are happening. 1, the velocity is negative, so the particle is still moving that direction.
Okay.
If we look at the dot down here on the position graph, at the same time, roughly, so I'm going to put it 4.5-ish. Close enough. The position is negative, so the particle is way over here on the left, in a negative position. At that moment, the velocity is negative, so it's still moving to the left. If you go forward in time to this moment, the particle is as far left as it will ever be. And at that moment, 4.848, the velocity is 0, so the particle stops. In the next moment, the particle starts to move to the right. That's why that velocity is now, come on, positive. But the particle is still over here in the negative half of its path. But it is moving to the right. Did that answer it?
Yeah.
2 more. Please.
So you said the instantaneous velocity is equal to the tangent slope
Of the position.
And so would the instantaneous acceleration be the slope of velocity? Or is that how you say that?
Yeah, perfect. And if you just turn the page, it says that same thing in your notes. Right here. So it's perfect. Page 3, yeah. The instantaneous rate of change of velocity is the instantaneous acceleration. Yep. 2 more for August. Okay, back to here. So we've got 4 done. Go to 5. Oh yeah, please, TJ.
Can you just tell us how to write our answer for 4?
This is exactly how, you can write it different ways, but this is the way I've seen most common on the AP test. And no worries.
Okay.
You're welcome. 2 more.
And you said that the tangent slope of position equals y values on the t.
Correct. I'll say that a couple different ways. So you can say the tangent slope of the position is the velocity. But the velocity is displayed as the y coordinates on the velocity graph. The time is always the x coordinates.
But the y value, the y coordinate changes with each graph.
So if I'm looking at the position graph, the x coordinates are still time. Like if I look at this dot LE, that's 1 is the time. Over here, 2 is the time. But on the position graph, the y values are telling me where the particle is located. On the velocity graph, the time is the same. But instead of telling me where the particle is located, the y value is telling me how fast is the particle moving at that moment and in what direction. 2 more. Cool. Back to here. Go to number 5. It says for the time interval 1 to 5, use the graph to determine if the position graph has a relative max. This is an abbreviation. I just write R max. You can use that abbreviation on the AP test, so I will use it all the time. R max and R min, or neither, so it's 1 of 3 possibilities, in the time interval. So brand new definition that you must memorize right here on the board. This is not in your notes, so you'll need to write that one down. Don't write anything yet, though. Like, make sense of it first, but don't write anything. Always. Make sense of it first. Once you make sense of it, you may be able to write a lot less. And then you have a much more compact note card. It says any function has a relative or local max. They'll use both words. They won't use them in the same question. Just one time they'll use local, some other time they'll use relative. But you have to recognize both. When that same function changes increase to decrease. So let's look at position, because we're looking to see if the position graph ever has a relative max or relative min. So if I follow position, I'm looking to see if, as I go along the position graph dot by dot, if from one dot to the next, I ever change from increasing to decreasing, or from decreasing to increasing. Raise your hand, please, if you can see in this time interval from 1 to 5, if there's ever a spot on the position graph where the position graph changes from increase to decrease. Raise your hand if you can see that. It's not supposed to be hard, it's supposed to be easy. Let's go, Trey.
Sorry, what was the question?
So we're looking to see if the position graph says any function, we're focusing on position, is going to have a relative or local max or min. So this is talking about max. Min's just the opposite.
Yeah.
When that same function, so in this case position, changes either increase to decrease or vice versa. So from 1 to 5, Trey, do you ever see the position graph changing from either decrease to increase or vice versa?
Yeah, 4.4.
Okay, that's all I'm trying to get you to see.
Yeah.
How many saw it? 47. 2 points, 3 for Trey. Does that make sense? Okay. So that's a relative minimum on the position graph, where the position went decrease to increase. Relative max is the opposite. Questions?
And they could ask you that, like if they were asking if velocity had a relative or local maximum, and they could like show you the position graph, and you'd have to determine if like the slope changes from like
There we go.
more steep to less steep.
So here's what August is saying. Look at position again. Look at position. Say it out loud as a class. Right here. Is the slope of the position positive or negative? Say it.
Negative.
How about here? Here. Here. Good. Whenever the slope of position is negative, the y values of the velocity are going to have negative values. So these are all negative values. Whenever the slope of the position is negative, the y values of velocity have to be negative because velocity is the slope of the position. Go ahead, Mary.
So is that like what your chart says? Like when it's decreasing, it's negative?
There you go.
Like the,
Yep.
is that what the I and the U
Yeah,
is?
take it from Aaron. If my position graph is going down, every value of the velocity will have to have a negative value. That's exactly what that means. Questions? Please.
I just kind of have a random question.
Yeah.
So on the velocity graph, when it's kind of like coming up at the end, that means it's like slowing down and then going the other direction, right?
Let me say it back to you, just make sure I've got it. From this point to this point, the velocities are all negative, but so I know I'm going left, but the velocities are becoming less negative, so I'm slowing.
So what if it doesn't slow before it switches? How can it cross zero?
In a real world scenario, I don't know how that could ever happen. In just a pure math problem, you could have a jump. You could have a velocity that came along like this and then suddenly jumped up here
Right?
to a new velocity. But I don't know how to have a real object do that.
Yeah.
2 points. Okay, back to what Marion was saying, and also August. So what they'll do on a test is they will not give you the position graph. They'll only give you the velocity graph. And you'll go to Danika's chart and you'll say, okay, I'm trying to figure out if the position, and this is how I do it. I draw the chart and I just circle things. I say, I want to know if the position ever changes from increase to decrease or vice versa. So I'm looking for the position to do this. Increase to decrease or vice versa. But I don't get to look at the position, I have to look at the velocity. So what I look for is, do the y coordinates of velocity, keyword y coordinates, do those y values of velocity ever change from being positive to negative or vice versa? Trey said that the relative min on position occurs right there, when position changes from going down to going up. At that exact same moment, the y values of velocity are changing from being negative to being positive. That's how you know that the position graph has a relative minimum.
Right.
And that's what you need to memorize. But I just memorized Danika's chart. I don't really memorize these words. I just use the chart. So, question? Cool. Here's what I would have written on a test right here. It asks for 2 reasons. There are the 2 reasons. 1, the position graph is changing from decrease to increase, so position has a relative min. But you can also identify that position has a relative min by seeing that the velocity is changing from negative to positive.
What does R and N mean again?
The R is just for relative,
Okay.
and they allow you to use that abbreviation, so I'll use it all the time. So. And sometimes they call it local instead of relative, but it means the same thing. Caleb, please.
If it doesn't ask for the 2 reasons, if you still have to list them?
No. More commonly, what's going to happen too for Caleb is they're going to give you just the velocity graph, and they'll ask, does the position ever have a relative min? And so I'd say about 98% of the time, you're just going to list the orange answer. It could be a rare question where you would write the other, but not very common. So.
And you can do like DC dot for, like they accept those abbreviations as well.
For which one?
Like decreasing and increasing.
Yeah. So these abbreviations are fine. The neg and positive are fine. The R min and the R max are fine as well. Two more for August. Just watching your pencils. Yeah, go ahead.
Do we ever have to find the value of the relative minimum, or just say that it has one?
Got you. For test number 1, the worst you would have to do is look at the graph and just count. Like you wouldn't be expected to get 3 decimals, but you could see roughly where it's occurring. And if it's a multiple choice test, you'd be able to pick out the proper one. You know what I mean?
Yeah.
So for now, you won't have to calculate this number. In Unit 3, we will learn how to calculate the number. Two more for Spencer. Okay, next thing. Another new definition. It says, use the graph to determine if the position ever has a critical point. Critical point, relative min, and relative max are not the same, but they're extremely related. Any function has a critical point when the tangent slope of that function is either 0 or undefined. So everybody in the room, raise your hand and answer this question. I'm supposed to be looking for a critical point on position. I'm looking for a critical point. I don't know an abbreviation for that one, so you have to spell it out. A critical point on the position graph. Raise your hand, please, and tell me. Says the position graph is going to have a critical point when the slope of position is either 0 or undefined. Where should I be looking to find the slope of position? Hands up. Where should I look to identify the slope of a position graph? Like, what's the easiest place to look for and find the slope of the position? Most idiots go, Emma. Go to the velocity. So Emma, I'm going to follow along here. If you knew that, 2, 3 for Emma. I'm going to follow the velocity graph. Is the velocity graph slope? Sorry, the y values of velocity are the slopes of position. So right here, this is negative. This y value. This y value is negative, negative. Okay, it's the same place again in this case. At that point, the velocity is 0. That means the position graph has a critical point at that time. That's the reason. Questions? Please.
So you said that the velocity graph is the slope of the position.
Every y value that you see on velocity is a number telling you the slope of the position graph at that same time. Does that make sense? Does that answer your question, Ellie? 2 more. Please, Jared.
There's a typo in that answer.
There is a typo. How many saw the typo? 3 points, 4 for Jared. Thank you. I've got an extra 4 right there. So it should just be 4.848, not 4.4848. Write that one down and fix that. So that will be an error in the answers as well. I did notice one other typo that I made in your packet. Right now, everybody look at me so you don't miss the typo. Right now, we're talking about the time period 1 to 5. Later in the packet, it will switch to the time period 0 to 4. But because I was copying and pasting, I forgot to change some of those 1 to 5s. So first half of the packet, it's always 1 to 5. Second half of the packet, it's 0 to 4. There's a few that say 1 to 3, that's different. But anywhere in the front half, say
0 to 4 is you want us to do.
it should be 0 to 4. Like, let's just go through it fast. Pack it up here. That's not going to help. Hold on.
There's only one of them.
so here's your packet. On page 1, it says 1 to 5. 1 to 5. Page 2, it's still talking about 1 to 5. So all the way to question 8, the time period is 1 to 5. Still 1 to 5 on questions 9 through 15. But then the formulas will change, and you'll start using graph B. That's when the time period changes. So when you're using graph B, it should be 0 to 4, 0 to 4. This table should be 0 to 4. So this is another one where I forgot to type in the dots on the table. So they should go like you see here. The answers have the right points. You can use that as a reference. The 1 to 3 is different. Just leave that as 1 to 3. But then we're back to being, it should be 0 to 4 for all these questions that involve graph B. That's all. Just say 0 to 4. I lost track if I was helping someone with a question. Pretty good. So, of course, left the pen in the back. Okay. Back to the packet. Any question about critical point? Another way to do that is with Danika's chart. Come over here and you say, okay, I'm looking for where a position has a relative min or relative max. I'm going to circle this. I'm going to look for this sort of change on position. If I can't see the position, I'm going to look on velocity for this type of a change in the y-coordinates of the velocity graph. That's relative min or relative max. If I'm looking for critical point, I can still use the chart. What I do instead is I say the position will have a critical point when the slope of the position is neither positive or negative. If the slope isn't positive or negative, there's only two other options. The slope is either 0 or the slope is undefined. We don't have any examples of undefined yet, so don't worry about that. We'll get to that later. In this packet, that doesn't ever happen. So all I'm looking for is on the position graph, is there ever a place where the slope of position is 0? I could have found that by finding the y-coordinate of the velocity to be 0. That's finding a critical point on the position graph. Cool, next thing. One more definition, and I think that's it for this packet.
Can I have a definition as well? Sorry.
Say it one more time.
You didn't?
Oh,
Never mind.
oh, you're good either way.
Okay.
No, just always tell me to go back. I don't mind at all. So that's the definition of a critical point.
And how would you find that on like the chart again?
So I'm going to do a different example this time, Ellie, to help reinforce. The definition says any function. So you will be asked later in the packet to find the critical point on the velocity graph, which means you're looking to see where the velocity has a slope that is either 0 or undefined. But the slopes of velocity are the y-coordinates of acceleration. So I'm looking for a critical point on velocity, but I'm going to look at acceleration and find where the slope of the acceleration is neither positive or negative. So that now is slope of velocity. So this y-coordinate right here of the acceleration is 0. That corresponds to a slope of velocity being 0. That's a critical point on velocity. The whole idea of this is they're going to continue to ask you to answer a question about one of the graphs, like answer a question about velocity, but do it using the other graph. This one shows all three, so you can see how they correspond. Right here, what's the slope of the velocity, Ellie? 0. That's why the y-coordinate on acceleration is 0 at the same time. 2 more. Please.
Did you ever explain what like CU or CB means?
Next one. 2 more for Jackson. So on to number 7. It says any function has an inflection point when that same function changes concavity. So the CU is an abbreviation for concave up. And concave down. And they allow that to be used as well, so we'll use those abbreviations.
Inflection point?
An inflection point is where the graph changes concavity.
Okay.
So look at position here. Just say it out loud, please. Would you say the position graph is concave up or concave down at that moment? Just say down or up. Say it. Down. How about right here? Say it. Yeah, it's up right there. So now look at the correspondence. When the position graph, this is the value of Danika's chart again. When the position graph is concave down, you will see the y values of velocity decreasing. So look here. I can see that every y value of velocity is going down. The velocity is going down, the velocity is decreasing. And precisely this moment right there, the values of velocity stop going down and the values of velocity start to go up. That's the moment when the concavity of position will change. Look over here. When the velocity was going down, the position graph was always concave down. Once the velocity switches and starts going back up, the position graph switches to being concave up. So here we go. Position graph is concave down all the way until we get to right there. When position switches concavity, that's an inflection point on position. But you can identify the inflection point on position by either looking at when the velocity changes from decrease to increase or vice versa, or when the y-coordinates of acceleration change positive to negative or vice versa, which is what's happening right here. That was kind of a mouthful, so I can say it as many times or differently as you need. Please.
So like for the position graph, the velocity graph is its derivative? Is that what that
That's
is?
correct.
Okay.
Yeah. I haven't really used that word yet, but we will start using it heavily.
Okay.
The velocity graph is considered to be the derivative of the position graph. It's a fancy word for saying every velocity is just a tangent slope of the position. That's all derivative means.
Okay.
Good with that? 3 more for Grace.
Can you explain that again?
So it's just a word that somebody invented that means tangent slope of. So if I say the velocity, remember when I'm talking about velocity, I'm not really talking about the time per se. I'm talking about the y-coordinates. The velocity is the tangent slope of the position. And somebody said, I'm tired of saying tangent slope, so I'm going to call it the derivative. So they'll say the velocity is the derivative of the position. But it means the same thing. 2 more. Okay. Questions? Oh, so if you're writing an answer for this, here's what the answer would look like. 2 different ways to identify where the position graph has an inflection point. Either by looking at the velocity changing decrease to increase, or by looking at where the acceleration changes negative to positive. Please.
I just don't really understand how you could tell from that chart to find the critical point. I know how to use the chart to find the other 2 things, but
I would agree with you that the chart is not quite as good on the critical point idea, but here I'll just say it again. If I'm looking for where, let's say, velocity has a critical point, that means I'm looking to find where velocity has a slope that is either 0 or undefined. So that part's not on the chart, I just have to memorize that. So right here, velocity has a slope of 0. That means at this time, velocity would have a critical point. I could have also found that by saying, oh, the y-coordinates on acceleration are the slopes of velocity. So right there, the y value of acceleration is 0. That means that's the time where the velocity has a critical point. So perhaps the chart isn't quite as useful for that. Good question. 2 more. Just watching your pencil, Lily's still writing still, so wait a minute. Cassie's out for the count. Oh, she's back.
Oh, no.
You're good. No worries. Sorry about that. I don't know why I say sorry. I did it on purpose, but it wasn't trying to be mean, so I promise. I've had some where I'll say their name like that and they don't respond. Like they're really out, so I just let them rest. Okay. Number 8, it says use graph to determine when the position graph is concave down. That one, back to Ellie's question, straight to Danika's chart. If I want to know when the position is concave down, I simply can find when the velocity is either decreasing or when the acceleration is negative. So right here, you start at time 1. You're supposed to look at the interval from 1 to 5. Start at time 1. The velocity is decreasing all the way until we get to that time right there. So that will be the span of time where the position graph is concave down. Please.
Just for the last question, for the second reason, is it A of t or x of t?
A of t. Back to the chart, we were trying to figure out when the position graph makes this kind of a change, Ellie.
Okay.
We're going to do it by paying attention to when the velocity makes this kind of a change, or the acceleration makes this kind of a change.
Gotcha.
2 more. Back to here. So this would have been the answer I would have written on a test.
For number 8.
For number 8. I'm looking to see, yeah, keep going, Clark.
Why wouldn't you do like you're doing it like right where it changes?
No, this one's looking for a time interval. So 7 is looking for a moment in time, because an inflection point is a given moment. 8 is looking for an interval of time. It says, hey, what's the time interval when the position graph is concave down? So I say, well, the position graph is concave down during whatever time that the velocity is decreasing.
Yep, that makes sense.
Better? 2 more, please.
So although like on the graph as a whole, from 0.202 to 0.3298, all of that is when the graph or when the position graph is concave down. Wouldn't we just put for our answer from 1 to 3.298 because that's where the like time interval? Or does that make sense?
Yeah, that's actually a mistake.
1 to 5.
You are correct. I did that wrong. Like I did what you just said. I looked at the whole thing and I kind of forgot about this. That's well said. 3 more. Yeah, please, Ellie.
So is the reason why on that expression that there's no less than or equal to, there's no equal to sign underneath, is it because technically when it's like neither concave up nor concave down, it like you can't have equal outcomes? Does that make sense?
I'm going to bring you a ticket for that one. That's how they mathematically define it, exactly the way you said it. That at that moment where the inflection point occurs, they mathematically say that the curve is neither concave up or concave down, and that is exactly why this is not an equal to symbol. Very good. we'll later talk about when something's increasing or decreasing. And for whatever reason, mathematicians have not come to the same point of clarity. So they actually will accept either symbol. But what I teach is just always use the non-equal version, because then it's right for concavity, and it's just as right for the other. So you don't have to sit and think about which one to use. So 3 more. I'll bring it to you, actually, Taylor, please.
How would you want us to write the time interval for the answer, because it doesn't start before when it starts out?
Yeah, I should have written time 1. And in that case, it actually should have been greater than or less than or equal to, because it would have been already concave down at that moment. Yeah, so the answer will be wrong in the back in that regard, because I did it wrong there too. So you're going to finish the blue. You have the information you need. It really will go fairly quickly. It's the same thing again a few times. So. You got it, guys.
Thank you.
Quiz next time. Thank you for your life.